Welcome back to Compute 175. We are still talking about sorting. We talked about bubble sort, selection sort, insertion sort, and very recently also merge sort. I'll just remind you a little bit about merge sorts. So in merge sort, basically we're given a container, let's call it an array, and we want to return the same array, but the elements ordered in an increasing order. And the way we did it, we split the array into two non-empty parts. Actually, we went right in the middle, and we divided into two. The first part, we called it left, where we have the first half of the elements. And the second part is called right, where we have the remaining elements. And the way we sorted it, so we split this in two, but we will do it recursively, split, 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 and then afterwards we merge back. And when you merge two sorted lists, it becomes a long sorted list. So the idea is based on the notion of sorting two, on merging two sorted lists, and you get a longer sorted list. We liked this algorithm because we saw that the complexity was in the order of n log n. Log n being the depth of the tree, divide by 2, divide by 2, divide by 2, and we stopped at one element. And n comes from the fact that the merge is in the order of n. So n times log n, or log n times n. So n log n. However, when we looked at the space required, we realized that the merge sort requires double the original space. The original space being n, we need twice n. And that wasn't very good because in many applications you don't have that much space. So we like the n log n, we don't like the space requirement. So can we do better? And yes, we can do better. So what we will do, we will try to take advantage of the n log n, and the n log n comes from the divide by 2. We'll try to do that. And this space requirement comes from the merge. So we want to do the merge. We will try to do something else. Okay, so the QuickSort comes to the rescue. The QuickSort operates by partitioning an array. I'm given again an array of elements that I need to sort in ascending order. And what I'll do, I will partition it into two non-empty parts around what we call a pivot. So the pivot is a central point that we select among these elements in the container, and we will put it in the right place such that it is a pivot element between two partitions, two parts. One is called small, the other one is called large. And in small, I have all the elements of the array that are smaller in value than the pivot itself. And on large, I have all the elements of the array that are actually larger in value than the pivot. Okay, so if I can do that, and I know the pivot is in the right place, the elements that are smaller than the pivot are not necessarily sorted. The elements that are enlarged in the right-hand side are not necessarily sorted. But if I sort them recursively, then when they come back, well, I don't have to merge anymore. I just have to concatenate. Why do I have to concatenate? Well, because everybody on the left-hand side is smaller than the pivot, and therefore they're smaller than the right-hand side, and everybody in the right-hand side, in sorted, they are larger than the pivot, and therefore larger than anybody on the left-hand side. So I simply concatenate them, and I'm done. And the concatenation doesn't require additional space. So let's see examples. Very simple example. I will tell you the details of the algorithm later, but here visually, I have a container. It's indexed from 0 to 6, so I have 7 elements. And you can see these values are not sorted. So I will select one pivot. I say I volunteer a pivot. You, number 1, you will be the pivot. Okay. So now I selected a pivot. Can be anyone, but for this case we will select the first one, and we will find its place in the container and put it there such that every element on the left is smaller than it and everybody on the right of it is bigger than it. So this is how we do it. So we will partition in two parts, and this pivot will belong to one of the two partitions. Let's put it in the first partition, and you can see that everybody on the left is smaller than it, but it's not sorted, doesn't matter, and everybody on the right of it is bigger than it, but than the pivot, but it's not sorted. Okay, so these are all the elements that are larger than pivot, and these are all the elements that are smaller than pivot, including the pivot. If I have some kind of oracle that boom sorts this first partition, okay, with QuickSort, we'll do it recursively, and another a call of this Mr. Oracle, the QuickSort, on the large will give me now the sorted version of that partition. You can see now I have 10, 40, 50, 60, 70, 80, 90, so they're all sorted. I don't need to merge these two to create a container that is sorted. I just concatenate them, put some glue here, and there you go, you have it. Okay, so actually it is done in place. There's no need to merge. Why I don't have to merge? Well, there's no need to merge because all these elements are bigger than the pivot, so they have to be on the right hand side. They will not mix and match here, and everybody on the left of the pivot, well, they're all smaller than the pivot, and therefore they're all smaller than any element in the right partition. So that's why we just concatenate them. We don't have to merge. Okay, and this call is done recursively. Eventually I have a stopping condition, and that stopping condition is that I have one element, and that element, it's the pivot itself, and there's nobody bigger than it and nobody smaller than it, and therefore it's sorted, and I can start concatenating, and I'm done. We'll see it later when we'll talk about the algorithm per se. So basically what is important to retain here is that this is my container. Okay, I split it, but I don't copy it in two parts. I just say here's the limit of where the pivot will be, and everybody on the right is bigger than that pivot, and everybody on the left is smaller than it. So what happens is that with QuickSort, I will recursively sort this part, and this is what I will get, 10, 40, 50. The other part is not sorted yet, so I will have to call QuickSort. Here it is, so this is sorted now, this is not sorted. I'll have to call QuickSort on the right hand side. How do I call it on the right hand side? Well, I have to tell it where to start and where to end in that container, and I will sort it. And when it's sorted, well, suddenly the whole thing is sorted, and I don't have to copy anything from here to here, don't have to merge, nothing. It's done. Okay? So, how do I do this? What I have to do is find a pivot that I will put in the middle. So I will swap it somehow, shift it, put it, move it to the middle, to its right place. Not really the middle of the container, but the right place where it will be at the end when the whole thing is sorted. And I just have to make sure that I have a partition on the left with values that are smaller than the value of the pivot, and a partition on the right where I have values that are bigger than the value of the pivot. That's all I have to do. So why do I select the first element and say you are the pivot? Well, I could select somebody else, but to select the best one, I'll have to traverse this container and figure out who's the best, and that will cost me at least an n comparisons or some processing. That's expensive, so it's easy to just take arbitrarily either the first one or the last one. There are many algorithms that do that. The majority is just take the first one and I'm done. Okay, so here is the idea. I need to rearrange the values in the array such that I have somebody called pivot that is positioned in pivot index. Okay, that's the index of the pivot. And all the values in positions that are before, so smaller than the pivot index, have smaller values than the pivot. And all the values in positions that are after the pivot index are all greater than the pivot itself. So when we do this, because we are rearranging the value, we have to do some swapping. We will only use a temporary variable like we did for the selection sort, the insertion sort, or the bubble sort. Remember, swapping is 3 instructions, and with 4 accesses to the container, that's exactly what we will do here. So basically, the array will be divided into 2 parts around this pivot, and that's why we call it a pivot. Okay, so it's a central point, kind of a central point, not necessarily the middle, as I said. I will call QuickSort on the first partition. Where's the first partition? It's in the array, starting from the first element until the pivot index -1, so the position just before the pivot index. And then I call it again on the second partition. Where's the second partition? Well, it starts from pivot index +1, so the position just after the pivot, until the end. Okay, so notice that QuickSort doesn't get as input, QuickSort partition doesn't get as input just the array. It also gets the position where I start, where I end, and we'll get back to that later. So visually what happens is you have this container, it goes from first till n-1. Okay, so first meaning first element, the index is 0. Okay, so from first to n-1, and then I will find a pivot somewhere in between first and n-1. I will call it pivot index. Okay, and then I will call recursively on this partition where all the elements are smaller than the pivot, and on the second partition where all the elements are bigger than the pivot. Okay, how do I do this? I will talk about few algorithms. I'll show you 4 algorithms. The first one is relatively simple, and then I'll make it a little bit better, and then I'll talk about 2 famous algorithms to do this. So usually what we do is, as I said, we take the first element to say you're the pivot, but other strategies are also valid. And then I will have 2 indices, one that starts from first, one that starts from n-1, and they will run towards each other. So they will traverse the container and run towards each other. And at any given time, the section between the first pointer and the last pointer, those elements are not visited yet, but those that I traversed, I make sure that anybody who is bigger than the pivot is right of the right pointer, and anybody that is smaller than the pivot is left of the left pointer. And the day they cross each other, I traversed the whole thing, and I made sure that everybody bigger than the pivot is there, and everybody smaller than the pivot is on the other side, and the pivot is right in the middle. Okay. So how do we do it again? So here it is. We have an element that we select as the pivot, which is the leftmost element. Okay, and we will work with 2 indices. Let's call it left and right, or L and R, left for left and right. And we have to always keep in mind where the pivot is. Okay, so as I said, the pivot is arbitrarily, we'll select the first one. So L and P, both of them, so the left and the pivot, are initially 0, or the first element, and R, the right, is the index of the last element. Now we will alternate. I'll move the right indicator, so the right index, and I will check every single element. If it's bigger than the pivot, then that's fine, it should be there. But if it's smaller than the pivot, say, you shouldn't be there, and I'll swap it with the pivot. So I'll swap it with the pivot, it means the pivot takes its place, and it, which is smaller than the pivot, will go to the position 0, where the pivot used to be. And then I start moving left, and the left starts moving, and if it finds somebody who is bigger than the pivot, well, it shouldn't be on the left, so I will swap it yet again with the pivot. And I keep on doing this until I reach the middle, or somewhere where the left and the right cross each other, and I'm done. Okay, so here are the details. Our goal, don't forget our goal, is to move one element which is special, it's the pivot, to the correct final position. That's where I want to have it at the end when the whole container is sorted. So I move it such that every single element that is smaller than it is on its left, and everybody that is bigger than it is on the right. So this is what we call partition, how to partition. Okay, so here's my container, and I want to partition it. What does it mean I want to partition it? It means I want to put the pivot in its right place, and everybody smaller on the left, everybody bigger on the right. So here's my L and my P, they're position 0, and here's my R for right, is at the last position. And in between left and right, I haven't visited it yet. Okay, I haven't started yet. Everything on the right of right is bigger than this pivot, and anything that is left of L is smaller than the pivot. For now, I have nobody because I haven't traversed my space yet. Okay. Now, the between L and R is not visited yet, and as long as I still have something in between, I haven't finished the partition. So now what do? I start traversing from the right, and I compare the element at position R. Is it bigger than the pivot 60? If it's bigger than the position 60, that's fine, I keep on moving. But if it's smaller than the pivot, so wait a minute, 50, you should not be there. Therefore, I will swap it with the pivot. And you can see now the pivot is here, it's indicated by P, and the 50 has been moved here, and my L moves forward. Okay, so now left of L is smaller than a pivot. Yes. Is there anybody right of R? No, I haven't seen anything yet. Okay, now what do? I still have to explore this part. Okay, what do? I move L. I keep on moving L. 30, yeah, it's smaller than 60. 10, yes, it's smaller than 60, so it's fine. They can stay on the left. 20 is smaller than 60, great. 40 is smaller than 60, yeah, that's fine. 90, whoops, 90 is not smaller than 60. You should not be there. Okay, so here I am. I'm pointing at 90. 90 should not be on the left of 60, so I will swap 60 and 90. There you go, I have a 60 here and the 90 there. And then I start moving R. I move R by 1 first because I put the 90 there, and I compare. Is 80 bigger than 60? Yes, it's fine. Is 70, whoops, is 70 bigger than 60? Yes. So now I keep on moving R, and then suddenly the R crosses L. You remember they were running again towards each other, and now they crossed. It means I finished traversing this whole space, and the pivot is in the right place, and everybody on the right indeed is bigger, and everybody on the left is smaller. So I'm done with the partition. And what do I return? I return this position 5, which is the index of the pivot. Okay. What have you noticed here is that this pivot that used to be in position 0 has been moved 3 times. I'm swapping it. Each time I'm traversing from the left and from the right, and L and R are getting towards each other. I am swapping this pivot many times. It works, as you can see here, but we don't like to do too many swaps because each swap costs us 4 accesses. But let's assume this partition is done. How do we write QuickSort? Well, QuickSort receives the data, the container that I need to sort, but I need to know where to start and where to end, to call it recursively in different parts of the container. So QuickSort alone, I cannot call it recursively, and therefore I will create what we call a helper function. A helper function here, I have the QuickSort helper, where I get the same data, but I tell it where to start and where to end. I start at position 0 and end at the last element, so I give it the whole container basically. But when I call the function recursively, I call it with the data and first position and the last position. Okay, initially it's 0 and length of data -1, but generally it's just first and last. If first is smaller than last, it means I still have elements in there. I don't have just one. If I have one, I'm done. But I have more than one, then what do? I have to partition it. So what do I partition? I partition the data from first to last, the same parameters as those from the QuickSort helper. Okay. Once I partition this, I get as output the position of the pivot. So I created two parts and the pivot in the middle. So each part has to be sorted by itself. So I call QuickSort helper recursively of the data starting from first till pivot -1. Okay, that's where I have the pivot, the position of the pivot. So until the element just before the pivot. And then I call again QuickSort helper of the data from pivot +1, the position after the pivot, till the last element. Okay, so suppose the pivot is here. This was my container from first to last. First to last, this is data. Partition will give me the pivot. Here's my pivot. Then I need to call QuickSort on this part from first till pivot -1 and from pivot +1 till last. That's exactly what you see here. Okay. That's if I have partition, but I don't have partition. We didn't write it yet. So if I have partition, this is very simple kind of function that I have here, a recursive call of QuickSort twice for each partition, but I have to partition first. So how do I partition? I showed you one algorithm. I'll show you a second one. The second one has the advantage of not swapping this pivot too many times. I will select the pivot, and it'll be the first one as well. Okay, first element, you're the pivot. I'll volunteer. You're the pivot. Nothing to say. But I'll leave it there. I'll leave the pivot in the first position, in the waiting room, and I start partitioning the rest of the section from position 1, so first +1, until the end. And what do? Basically, I will have also two indices from the beginning and from the end racing towards each other. And instead of swapping with the pivot, I said the pivot stays in the waiting room there, I'll swap the first element from the right that I find smaller than the pivot, and the first element that I find from the left that is bigger than the pivot, I'll swap those two. And then I keep on going. Oops, swap those two. Keep on going, swap those two. And at the end, when they just cross, that's the position where I have to put the pivot. That's when I find somebody that is actually smaller than the pivot. And I'll take that one, take the pivot, swap them, and I'm done. Okay. So I'll show you how this algorithm is. I just explained it. So partition, I get the data and the first element and the last element. First thing I do is take the first element, copy it as the pivot value. Okay. It's still there, but I have the value of the pivot in a local variable. Then I have the mark from the left, which is first +1, so just one after the pivot. The pivot is still waiting there. And then the right mark is the last element. And while I'm not done, I'm trying to race this left mark and the right mark towards each other. So in the beginning, I'm not done, and therefore I'll say, well, done is false. So while not done, what do? Well, I have another loop that says while the left mark is still smaller than the right mark, so they haven't crossed each other yet, and the data at the left mark is smaller or equal than the pivot value, so that's fine, leave it there. So while it's there, move forward. Left mark is equal to left mark +1. So my left mark is moving towards the right mark that is still waiting. So once I stop here, why did I stop here? I stopped here because suddenly the left mark has crossed with the right mark, or actually I found an element that is bigger than the pivot. Okay, so my left mark is indicating an element that is bigger than the pivot. Then I stop there and I go and I do another loop to traverse from the right. So while the right mark is still bigger than the left mark, okay, they haven't crossed yet, and while the data at the right mark is still bigger than the pivot, it's in the right place, it's fine, I move forward. Right mark is equal to right mark -1. Why -1? Because I'm going towards the left. Okay. When I finish, same thing. Either they crossed, or basically I have the value in the right data of right mark that is smaller than the pivot. And it shouldn't be there. I have to move it somewhere else. I have to move it on the left of pivot. So I check. If they crossed, the left and the right mark have crossed, then I'm done. I'll stop to get out of this loop. And otherwise, what I have to do, I have to swap those two elements, the one that is on the right mark, which is smaller than the pivot, and the one that is on the left mark that is greater than the pivot, and I swap them. How do I swap them? Well, you know the three instructions. Temp is equal to data of left, data of left is the data of right, and data of right is temp. That's a simple swap. So I keep on swapping them because they're not in the right place. Then, when I finish this loop, I basically have the right mark, which is indicating an element that is smaller than the pivot, and I will swap it with the pivot. Okay, so I will say, hey, because pivot is in position 0, I will say temp is the pivot, the data at first, and the data at first I will put the one that is right mark, and then the data at right mark I put the temp. This is the typical swap. Okay, and then at the end I need to return the position of where the pivot is, and the pivot I just put it in the right mark, so I return right mark. Okay, so this is the partitioning. Notice that this algorithm here in Python, I could have put it right here, but it would complicate the QuickSort too much, and that's why it's better to just assume I have a function, I call it, and then I write that function. It's way easier to maintain it, it's way easier to understand the code, and if later you say, I don't like this algorithm, I will use the Lomuto algorithm or the Hoare algorithm, those two that I'll show you later. Then it's very easy to just rewrite that function here, and you don't have to rewrite the QuickSort, you just rewrite the partition. So it's a good practice to have these functions that you call, and then you have to implement them separately. You can also test them in isolation separately from all the code. Okay, so what is the complexity of the QuickSort as we implemented it here? What is the best case scenario? The best case scenario, you think it is when the container is already sorted? No, it's not the case actually. The best case scenario is when I am extremely lucky. When am I lucky? Well, when I'll take the pivot that by chance, the first element, and I say you are the pivot, it happens to be the one that perfectly separates in two partitions of the same size. Then I'm dividing actually by 2. And next time I'll go in one partition, I'll select the pivot, it happens to be the one that is perfectly in the middle that separates it into 2. So if I'm very lucky, this is what will happen. N will divide by 2, and this one will divide by 2, will divide by 2, will divide by 2, until I have 1, 1, 1, 1, 1, 1. So what is the depth of this tree? It's like in the, remember the in merge sort as well in binary search, when we have a tree like that, this is the number of times I divide by 2, n divide by 2, 2, 2, 2, 2, 2, till I reach 1. That's the logarithm base 2 of n. That's the depth. So the depth of this tree is logarithm log of n. But in each level of this tree, I have to do partitioning. And what is the partitioning? I have 2 counters that are running towards each other, traversing the whole container, which is n. So the partitioning is of complexity n. So it's log n times n. And that's why we call it n log n. That's in the best case scenario. We have n log n. N log n is way better than n squared, which we had for selection sort and insertion sort. And it's the same order of complexity as the merge sort. So we succeeded in keeping the n log n. But what is the worst case scenario? The worst case scenario is actually when you give a container that is already sorted. If I give you a container that is already sorted, and let's show you the picture here. Here's my container that is, suppose it is already sorted. Then when I select the first one and I say, hey, you are the pivot, everybody else is bigger than it. So when I partition, I will have one element on one side and n minus 1 elements on the other side, because they're all bigger than it. There's nobody smaller than it to be on the left. And then this n minus 1 elements, they're already sorted as well. And when I select the first one and I say, hey, you're the pivot, everybody else, the n minus 2 elements, will be larger than it. And then I do the same thing, I do the same thing. So finally, the depth of this tree is this path, and this path is n minus 1, n minus 2, n minus 3, n minus 4, n 1. So it's actually, it has a depth of n. And in each level, I do a partitioning. The partitioning is order of n. I have a depth of n. It becomes n square. So the worst case scenario, my complexity is n square. That's not very good. So whenever I have a sorted container, or reverse sorted, or nearly sorted, almost sorted, my complexity is n square. Actually, when it's nearly sorted, it's better to call insertion sort than QuickSort. What is the average complexity of this algorithm? Well, it's beyond the scope of this class, but it has been proven that the average case, the number of comparisons that we will have to do, is in the order of 1.4n multiplied by log n minus almost 3n. This can be rounded to basically n here log n minus something n, doesn't really matter, and this multiplier doesn't matter. So we can say that the average case has a time complexity of order of n log n, so very close to the merge sort. Actually, it is the same as the merge sort. Here it is, I have the base case scenario is n log n, the worst case scenario is n squared, and the average case scenario is n log n. This is very good. And in addition, I don't have to copy from one basket to the other. Remember, there's red and black baskets. I have two partitions, and then to merge them, I needed this green basket. Here, I don't merge. I just concatenate. So I'm doing the sorting in place, and therefore I'm just using the container as a space plus one, this temporary variable, to do the swap. So that's perfect. Now, I showed you two algorithms for the partitioning. One where I kept on swapping with the pivot, such that I make sure that nobody is smaller than the pivot in sitting on the right, and nobody's bigger than the pivot in sitting on the left. I swap them like that. The second approach, I left the pivot waiting in the waiting room in position 0, and I swapped those that are either smaller than the pivot and still sitting on the left, on the right, or bigger than the pivot and sitting on the right. I swapped those. Okay, so I have less swaps of the pivot itself, and therefore the second approach is better. And there are many people who worked on other algorithms and tried to prove it mathematically that they have actually on average less swappings than other algorithms. Why less swappings? It's not a term, it's not the comparisons, it's the number of swaps. Because the swaps are expensive. Each time I do a swap, remember there are 4 accesses to the container. So I'll show you one famous algorithm called Lomuto partitioning. And the Lomuto partitioning is actually very short. It's just one loop here. What do? I have the pivot, and I'll choose being the last. So the last element, so A is my array that I want to sort, and I have first and last are the two extremities. So the pivot, I'll choose it to be the last. And then I will traverse from the first element. So I is the first. So I have an indicator basically that is telling me where is the position that I'm putting things in, and I will traverse J here. You can see J in the loop will go from first till last minus 1. Okay, last is the pivot, as I told you, I'm designated as pivot, and I will traverse from first till the element just before it. If the element at position J is actually smaller than the pivot, okay, then I will swap the element at J and the element at position I, and I move I by 1. Okay, so any element that is smaller, that I find here, that is smaller than the pivot, I will make sure that it's actually going to the left. Okay, and whoever was here, was at position I, will move to where J is. And I move forward. At the end, I will swap the pivot with the position AI. And I'll return I, because I is now where the pivot is. So again, last is the pivot. I traverse the container with J and swap any smaller than the pivot to position I and increment I. At the end, I is the position of the pivot. It seems very simple, and it works. And people have shown that this approach does less swaps than the two others that I just showed you. Okay, so the position I of the pivot is guessed from the left to the right. When J is traversing, it is trying to guess where is the final position of the pivot, which we will call I. Okay, so J is scanning the whole array from the beginning till the end. When the swap is done, then I have a new position for I and so forth, and at the end that's the position of the pivot. Now, there is another algorithm that appears to be 3 times faster. It has 3 times less swaps than the Lomuto, and this is called the Hoare partitioning. Hoare partitioning is again named after the person who came up with this algorithm. I will also designate the first element as pivot, like we did with the 2 first algorithms. And then I have also a left and the right. So the left starts at first minus 1. So it starts actually before the container. And right starts at the last plus 1. So I'm starting outside the container. And then while it is true, so this is kind of an infinite loop, I have 2 loops inside, repeat until and repeat until. So what do I repeat? I repeat moving the right-hand side, okay? Right-hand side is moving towards the left-hand side, and the left-hand side, you'll see later, will move towards the right-hand side. So the 2 indices from the 2 ends, actually, they're running towards each other until an inversion needs to happen. So when does it happen? Look at this here. I will repeat decrementing R is equal to R minus 1, until the element at position R is actually smaller than the pivot. Then I stop. And then I will move L plus 1 towards the R until I find an element in position L that is greater or equal than the pivot. So I found somebody that is smaller than the pivot with R, and I found somebody that is bigger than the pivot with L, and I see if L is still smaller than R, they didn't cross, then I simply swap them both. Okay. Otherwise, I will just simply return R. Say that's the position. Okay, and R will have the pivot that I started as being the first. Okay. Otherwise, I'll go back here. It's not finished yet. I'll run R again towards L. I will run L towards R until I find somebody who is in the wrong place. So AR is actually smaller than the pivot, and AL is bigger than the pivot. And if I haven't crossed L and R, I will swap them again. Okay? And otherwise, I am done. If they cross each other, I am done, and I return R. Otherwise, I do it again, do it again, do it again. The return is what takes me out of this infinite loop, because it's taking me out of this function. I return R. Okay? So Hoare partitioning apparently has an average 3 times fewer swaps than the Lomuto's partitioning, and the Lomuto's partitioning is better than the first 2 algorithms. Okay, so in summary, basically you have an index L and index R that run towards each other until they cross, and when they cross, R will indicate the position of the pivot. And basically what I'm doing when they're crossing, it divides the the container into two partitions, one where all the elements that was scanned by L, all the elements are actually smaller than the pivot, and one that is traversed by R, where all the elements are bigger than the pivot. Okay, each time I find R finds somebody smaller than the pivot, and L finds somebody larger than the pivot, they are swapped. Okay, that's how it works. Okay, I hope you enjoyed this magic of QuickSort. QuickSort is a beautiful algorithm, amazingly fast. It is the algorithm that is implemented within Python when you type sort or sorted. On average, in general, it's way faster than any other algorithm, but in some cases, especially when the container is almost sorted or sorted, it's really lousy, it becomes n square. So if you know your data, you have data that you have sorted before, and you are just adding few elements, don't re-sort with QuickSort. You can sort with something else. It will be more efficient. Otherwise, yeah, you can count on QuickSort. It's very, very, very fast. This shows you as well how when you write your code, if you write modules, like partition is a function, a module, separate module that you can do separately later. If you decide to use another algorithm for partition, you can do it very easily if you created a module for it. So these are lessons to learn when you are programming. Yeah, and again, you see the power of recursion, how elegant these solutions are with recursion. Very few lines, and it happens by magic. Another thing that you need to remember, despite the fact that merge sort was dividing in two perfect partitions, the left and the right were almost the same size, in QuickSort the two partitions don't have to have the same size. One can be way bigger than the second one, and so forth. In the worst case, you have one and all the others on the other partition. That's bad. You don't want that. You want the best case to be a perfect division by two. You can't always have it, but in general, when it's random, QuickSort is fantastic. Okay, I'll see you in the next lecture. The next lecture, I believe, we'll be talking about trees, a different data structure.